I will start with a big news, fresh news from yesterday. NVIDIA paying a 9-digit sum for synthetic data. And that's basically not surprising because many AI experts, even Elon Musk, agree that the future is with synthetic data. So I hope you will listen to my presentation today, because I will talk about synthetic data that bridges the gap between AI innovation and privacy. My name is Ivona Krchová, and I am senior AI researcher at Mostly AI, which is a synthetic data company. So, what do we see currently in the market? Or not currently, the GDPR is with us, I think, since 2018. But the demand for data is increasing, and also companies are collecting more and more data. And the companies and the research, all of that, they need it for the AI, for the automation, for analytics. But at the same time, there are regulations. I already mentioned GDPR, but there are others in other countries. Currently, we are talking about AI acts, and there is also ethics that comes and that restrict the models. On one hand, I think it is bad because when you have a restriction, you do not have access to data, you cannot innovate, and you cannot develop. On the other hand, I think that everybody agrees with me that you would not like to share your sensitive data. You would not like to share your healthcare data. And that's the reason why the regulation come into the place. So you as a data scientist, how would you anonymize data? What you would do in order to protect sensitive information in your data set? Any ideas? Remove. Hashing. Okay, great. Exactly. So I think first thing that come to your mind would be, yeah, so it contains sensitive information, so like I do not need it for my statistical analysis, so let's remove it, right? Because we know some personal identifier information, PII, and we don't need it to develop the model. So we can just simply remove them from the data set, and that's all. But the problem is that it is not enough. And it is not enough because in the data set exist quasi-identifiers. They alone, they do not identify a person, but if you combine them together, they do. So some of the examples. 80% of data subjects are identified by free transactions, even when only a merchant and the date of transactions are revealed. The other thing is 63% of the US population is uniquely identifiable by combining the gender, date of birth, and zip code alone. And that's a lot. So there are other methods that you can do. You can do some permutation of your data. You can do some randomization, so you put some noise to your data. Or you do generalization, so you are grouping some information all together. So you have some, if you have some specific information, you group it. So in case of, let's say, age column, you can say, okay, I will bin them, or things like that. However, there are a lot of research done showing that this is not enough. Like in the era of big data, such methods simply does not work. So what is happening? Basically, you are collecting data. You have a lot of data. You have value in your data. But then, if you want to share it with the research, you want to share it with consultancy, whatever, you cannot do it with the production data, or you should not do it. And you would anonymize data, and the value of this data is decreasing. And with that, the gap for the innovation is growing. because there is a privacy utility trade-off. You can either anonymize your data fully, which will be good, that the sensitive information will not be revealed, but on the other hand, like, there will be no value for you for any statistics, for any development. The other way is that the anonymization will not be sufficient. And that's like what we are seeing in the real life, because then the data will be vulnerable to various attacks. There are linkage attacks, inference attack, attribute inference attack, membership inference attack, and others. Just to mention, one of the most popular linkage attacks is a Netflix program. I don't know if you heard about it, but they show some anonymized data. They use it for some hackathon. And then researchers came and showed that they can re-identify people in this data set. How? They did it using those quasi-identifiers that I was talking about, because they could link this original data set with other data set that was freely available. In one case, they link it with Internet Movie Database. In the other case, they link it with the Amazon reviews, and they were able to identify people. And that's the issue in current big data era, because you have a lot of data, and you can do this linkage attack quite easily. And that's the issue, and that's why classical anonymization basically does not work. So that's why synthetic data came. So just to say something, what I mean by synthetic data, because synthetic data is fake data, right? So it can be random data. You can follow the shape, but the value of this data is not big. You can use it. You can use it for software testing, but for development, not really. You can use self-generated data. It's better. You already have some correlation between eyes and nose, but it's not scalable and it's not perfect. Model-generated data, if you have rule-based data, that's, again, improvement, because you have collections of head shapes, you have collections of eyes, nose, etc. You have some rules how they should be placed in your face. And then you can generate synthetic people. However, here is an issue that what comes in, it comes out. So there is no innovation. There is no new faces. So this is why AI-generated data is used. AI-generated data works differently. You use your source data. The algorithm learns all the patterns, correlation, structure, and then when it has this knowledge, you can generate as many as possible, as many as you want faces. In this case, this face was not part of the training data set, but it looks like real, right? So it is in this thing. You cannot determine if it is real or synthetic, but but you can use it. What I will touch in the talk today is tabular synthetic data. So I will not talk about faces. I will not talk about images. I will talk about datasets. And why privacy preserving? As I said, you have your real data. It contains sensitive information, and until now, your data is private. Then you can use it for the model to train on it and to get all the patterns, and you can generate the synthetic data. And this can be freely used because it does not have any one-to-one link to the original data. You can generate as many as you want. So that's the main difference between classical anonymization and synthetic data. Because if you do the anonymization, you still have this one-to-one link. You have your original record. You are doing something, some grouping, some some noising, some hashing, whatever, but you still have the link to the real person. When you use synthetic data, you do not have a connection to the real data. You use this data to train the model, but you do not have the connection to it. And that's why the synthetic data is basically, from my point of view, the way how to do the correct anonymization. Sorry. And now I will talk about the algorithm, so like here. And I will describe the algorithm that we developed at Mostly AI. It's called Tabular Argon. And it was published a couple of weeks ago. We published a preprint together with my colleagues. And just to give you an understanding where we are. So basically, the generative models are used in order to generate to learn the density estimation of the density function, right? And the generative models can do it implicitly, like a GANs, or explicitly. One of the possibilities is the diffusion models that we covered in the previous talk, where you have this iterative denoising function. Or currently, there are autoregressive models. Transformer as an example. This is the fundamental model in the LLMs. And so I do not have to say that it is powerful. In our case, we also use autoregressive model, but in a different way than LLMs. In LLMs, you treat the records as a sentence, so you do it token-wise, and you generate the next token based on the previous ones. Here, and it doesn't understand or it doesn't cope with the structure of the original data, with the range of age, with the possible categories that you have in your categorical columns. But the tabular argon does. So I will go through the models and I will try to explain it to you. So the autoregressive model is used to estimate the joint distribution by splitting it into the smaller pieces into the product of the conditional probabilities. And that's what we also do here. First of all, I will describe a fixed order training. So let's have a data set, a simple one, a patient data set with 3 columns: age, gender, and blood type. What is important to say that our model is working on the categorical use this x1, x2, x3 as categorical values. So we have encoding of any data types, datetime, digit, geodata. So we do a mapping onto the one or multiple categorical columns. So then the infrastructure is working on the categorical columns, and we can use one loss function, namely cross-categorical entropy. So that's a side note. However, how it works. So basically, in the training phase, we have x1, x2, x3. It goes through the embedding layer, so we embed the encoded data into the high-dimensional embedding space. Then we concatenate that together. We use the permutation masking layer, which does the job for autoregression. That means that if you are working with the column x1, the masking is full of zeros, so you do not have any information of any other columns. So you have the vector of zeros. This goes through the regressor block, which is feed-forward layer with ReLU activation function. Then it goes to the predictor layer with the softmax. And this basically, as I said, you have categorical data, so it predicts you the probability of any of those categories in that column. So you get this probability x1, the marginal distribution. Then for x2, again, embedding layer, then permutation masking layer. In this case, you have the information about x1. You don't know anything else, so you have zeros. And again, it goes through the regressive predictor, and you get the conditional probability distribution of x2 given x1. We use teacher forcing, so that means that we fill in the real data, not the one that is predicted. However, as you can imagine, the fixed order is not flexible enough. And for multiple use cases that I will share with you in the last section of the presentation, it's a drawback because I will share it later on. So we came with any order training, and what is different? The difference is that this permutation masking layer is used differently. In each batch of your training, we use different ordering of the columns. So each batch gets different permutation of your data, and this is done via permutation masking layer. So the first column can have masking, so it can mask out everything, or it can use the information from x2. It can also use information from x3, or it can use information from x2 and x3. So you basically modeled all the conditional probabilities for x1, marginal one, but also conditional one. And that's quite powerful because then you can use it for multiple use cases, which I will share with you. And that was training. So how the generation is working, again, this is the generation phase for the fixed order, but you can imagine you can do it for the any order as well. You just define the order in which you want to generate. So how it is done? As a starting point, you have the embedding layer and masking full of zeros. So you get a zero vector. This goes through the regressor predictor. You get your probability distribution for column 1. From this probability distribution, you randomly sampling, given this distribution. You have your sample, and it goes to the embedding layer. And again, you embed that, you use this information, you concatenate it with zeros for other columns, you go through the regressor predictor, you get your conditional probability for x2, you randomly draw, and again. So you conditionally generate one by one, column by column. So that's flat model. Flat model, what I mean by flat model is that like each row contains information about one user. So the users are independent. In the sequential data, your rows are dependent. So there is a time dependency. And the autoregressiveness comes along those two dimensions. So it goes from column to the column and from time to time. So let's now focus on this question mark. So you want to predict what is the body weight of the last visit of the patient. So what you have until now, you have all the information of the visits that were before, and you have also the information of the day and of the blood pressure. So for the columns, it works as I explained before. For the history, we use a so-called history encoder, which is LSTM, and you get this information. So then you model again conditional generation. So in this case, body weight at this timestamp 4, given the information at the timestamp 4, and also all the history of the date, systolic blood, and body weight. And you can say, okay, but I want to know also like to which person or about which person we are talking about, right? So there is another dimension for autoregressiveness, because you can add also the information about the patient. So you have information about the doctor visits, but you have also information about the patient itself, which has an effect on the outputs in the in the sequential table, right? So again, we use so-called context processor. So you encode this information and you predict the conditional generation given everything what you have. And this can be extended even further, right? So it doesn't have to stop in the two-table setup, because you have patients, you have his doctor visits, and for each doctor visit you can have prescriptions. So it works also with the nested sequences. Or you have doctor visits and you want to model insurance claims. In this case, you can again embed these doctor visits together with the patient and generate insurance claims. In the paper, or for the paper, we did a study and we compared our tabular argon against SOTA methods. We did it for multiple datasets and for multiple datasets for flat table and for sequential table. I'm just showing 2 examples. And we compare the quality of data, so the accuracy of synthetic data, meaning how close they are to the training data, how similar they are, and the training time, because as you saw, the architecture is not very difficult compared to the big models. It's relatively simple, and it comes with the efficiency, because the training time compared to other methods is really smaller, but at the same time the accuracy was comparable as well. So this is what I wanted to share about our algorithm. Yeah, that's also text extensions. I will not go into detail, but don't worry, we also take LLMs. It can be used. In our case, we combine tabular argon and we can call it language argon, so 2 models that cooperate with each other. And why we would use it, for example, your dataset can contain text column, and in this case, how to generate that, right? If you generate it as a categories, it will not be enough. It will not have this diversity. So that's why we use language argon. All right, so use cases. Sorry. So there are like many use cases. I will cover some of them. For me, like open data and free data sharing, so the privacy. If you have private data, you can collaborate. So that's one of the top use cases. Then you can train your model on synthetic data, and you can create fair data, and you can explain your model with synthetic data. So let's go into the use cases. So one of our customers, they wanted to share their data with the full company. What they said, for everyone from the intern to the CEO has access to data. So they share it, the synthetic version of it, so anybody could analyze the data. The other use case was Humana use case. Humana is a big American insurance company, And what they did, they synthesized the data. They use it for some hackathon or something like that. So people could use it for a development, and for it was done for data collaboration. It was quite nice. And then there are also other use cases that might be interested for data scientists. So imputation. If you have missing data in your data set, since the model learns all those probabilities, it can be used also to impute your missing data. So I will show you the graphs. So let's have the distribution of the H column. It is the black one, the original one. Then what we did, we synthesized the data, and sorry. So we had the original data. Then we manually remove some of the data. Namely, we remove mainly older people, and this shifted the distribution to the left. So now we have original data with NAs. Then we train our model, and we created the synthetic version of it. So the synthetic version also contains the NAs. So the distribution was nicely recovered. And what we did afterwards, we imputed the data. So we had all other attributes of the people, like what is important here for the age, like whether the people are married, in which position they work, and so on and so forth. And based on that, the model was able to impute the data. And what was nice, we came to the same distribution as before we created the missingness there. What is also very nice for the imputation with our tool is that when you want to impute, since you have this probability distribution, you can create multiple imputations. So if you create multiple imputations, let's say you impute it 100 times, you get a full distribution for that particular person, and you get the distribution of the H column. So you have the distribution estimate, and you can actually calculate some point estimates, such as mean or median, and you can compare it then with the actual value. This is what we done in this study. But that's just additional information than you can get with the imputation when you're doing with synthetic data. Upsampling, that's the use case we talked about in the previous talk. We did it as well. We did it on the tabular data, as I said. And we compared with some traditional methods such as small-t or naive upsampling. And what we saw that when we had really huge imbalance, in this case it is 0.05%, we saw the improvements. So when we generate the synthetic data for those minority classes, we were able to improve the performance of it. When the imbalance was like around 2%, 3%, we were on par with other upsampling methods. My favorite one, fair synthetic data. So in our data, there is a bias. So based on the collection, how we collect the data, there might be a bias. One of known or described is the bias, for example, between men and female, right? That let's say females in this data set, it was that females has lower income than men. And you would like to change that. So basically, if you have your data, you can train the algorithm on that, and you can create a fair synthetic data. How would you do that? Since you have your sensitive column, which might be a gender in this case, and you have your target column, which would be income, you have a distribution of the score so the probability that such person will have high or low income. And you have different distribution for female and for male. If you want to do it fairly, you can transform your distributions so that they are similar. They will not be the same, but similar as much as possible. And in this case, what we did in our study is that we, after that, trained the prediction model on this fair data. And what was nice, it was seen that the prediction of the model trained on this synthetic fair data are also fairer compared to the original data. So you have that. But ethics come with the cost. So if you change your data on which you train the model and you push it to have the higher income for your females, on the original data, you basically create more mistakes because your model will predict, oh yeah, it should be high income for this lady, right? So this comes with the cost, but it is ethical. So it depends what is the objective. The last one is explainability, because as we all know, it's sometimes quite difficult to explain what our model does, which features are important. So what we did, we trained the model on the real data, and we tried to explain the real data with sharp values, right? So here is a feature importance. So we show like which of the features are more or less important for the prediction. However, when we did it with the synthetic data, since it contains the statistical information, all the patterns, etc., we saw that the feature importance are comparable. And that's also a nice use case, because when somebody create the model on the production data, on the original data, and somebody else wants to use this model and wants to understand what is behind it, but doesn't have an access to the original data, the creator can create the synthetic data, and then the user can explain the output of the model using those synthetic data. And that's it for now. So what I forgot to mention is that our model, this framework that I described, is implemented in the open source synthetic data SDK. So you can use it with pip install. You can download it from GitHub repo. So I share the link here. If you like it, give us a star, please. Some marketing from my company. And if you want to know more information, check our blog, or we have some hands-on tutorials how you can use the synthetic data and how you can use our generators. This is also this you can also find on the GitHub repo. Thank you.
Thank you for a great talk. We have a lot of questions here as well. And the first one is, what dimensionality of the embeddings did you use compared to the input data?
Yeah, so basically there is a, I don't know the formula right now, but if you have categorical values, right, you have your categories 1 to 10, and then we embed that to I think 6 dimensional vectors. But if you have more categories, it increases, so we have increasing function, but it is up to 12, I guess. So from 6 to 12.
Cool. Is there a maximum similarity to the original data you can reach so that the anonymization is not compromised?
Yeah, that's a great question, because to have a private data, the objective is that you want to be as much similar as to your real data as possible. And this possibility is that you don't want to copy your original data, because in this case it will be not private anymore. So there is a margin, like the value of the original data is X, but you cannot get the accuracy of your synthetic data equal to 100, because in this case, you can use identity and it will be perfect, a synthetic data generator, right? So what we did, we also put there some privacy mechanism like dropout and other, and this decrease this quality of synthetic data such that some rare categories, for example, such as president as a occupation, will not be in the synthetic data, because there is only one president, so it will not be part of the synthetic data, and you cannot achieve 100% accuracy. So 98, it depends on your metric.
Thank you. When training a generative model on PI data, do you treat the model as PI as well? If the user demands deletion, do you have to delete the model?
If you when you need to delete?
When you're training a generative model on PI data, do you treat the model as PI as well? If a user demands deletion, do you have to delete the model?
No. So the model itself you can use. So basically, the data you cannot do reverse engineering of your model. So you cannot reversely. It's not just inverse function that will create you the original data on which you train. So the model itself, like, contains all the weights of those layers. So this can be freely used. It is actually what we are doing at the company, because we have our platform. Somebody can generate or train the model, and you can just share the generator with anyone else in the zip file or through the platform, and anybody else can generate the synthetic data afterwards. So there is no deletion of the model. It's a deletion of training data that you do not use after you train the model.
Excellent. Thank you. How the similarity of the synthetic data set compared to real one is computed?
Yeah, so there are different metrics. We also have our tool to calculate that, and if I say it in a simpler words, you compare the distributions. So you have you are comparing the distributions, marginal distributions or bivariate distributions. So joint distribution, you can do it like in any dimensions, but like then it will increase in time. But quite regularly, what is done, you compare the marginal distribution and bivariate distribution, and for the usability of data, what you do is that you split your training data or the original data into the training and holdout. You train on your original data and you evaluate on the holdout that was not seen in the training, and you train the model, synthetic model, on the original training data, and you evaluate it on the holdout. And if the accuracy is comparable, you know that your data is good enough. There is a drop again, since you do not have everything, but like the drop is really, really marginal.
Okay. Let's do two last questions. There is plenty of them, so we cannot go through all of them. But
that's good.
The next one is kind of funny. So the question is, how can I be also this smart when I grow up? What's the secret?
No.
Let's get to the next one. How can we ensure that synthetic data preserve a specific property of the original data we want to study?
It contains all the statistical information. So if it is statistically relevant, it will contain this information. So if you think it does not, let's try it and give us a feedback, and we will try to improve it so it will.
Sounds like a good response. Okay, everyone, that was Ivona Krchová. Amazing talk.
Thank you. Thank you.